Hello everyone. In this project I am solving a very practical problem on multi-GPU servers. When multiple jobs compete for GPUs, blindly assigning devices can be a huge mistake. For example, a 2-GPU training job might get placed on GPUs connected only over PCIe at around 16 gigabytes per second, instead of an NVLink pair at around 600 gigabytes per second. That can make gradient communication drastically slower. So the goal here is simple. Nobody should have to manually inspect NVIDIA-SMI and hardcode CUDA_visible_devices. Now moving on to how the system works. The user submits a job in JSON format. In that JSON, they specify the framework they want to run, such as DeepSpeed, TorchRun, Accelerate, Ray, or plain Python. They also specify how many GPUs they need, the minimum VRAM required, and whether the job needs fast GPU to GPU communication using needs_peer. Once the scheduler daemon receives this job, it filters GPUs based on available VRAM, then scores all possible GPU groups using the topology matrix. After that, it picks the best set, ideally the NVLink connected one, and launches the framework process using fork and exec, while automatically setting CUDA_visible_devices to the selected GPUs. Now let's see why topology actually matters. Suppose GPU 0 and GPU 1 are connected with NVLink, so that pair gets a score of 100. On the other hand, GPU 2 and GPU 3 may only be connected over PCIe, so that pair gets a score of 10. Naturally, the scheduler will prefer the pair 0,1 over something like 0,2 because the topology score is much better, and in practice that means much faster GPU to GPU communication. Now moving on to the topology matrix. At startup, the daemon queries NVML for every GPU pair and builds an n times n matrix of link scores. For example, NVLink might be scored as 100, GPUs behind the same PCIe switch as 50, and cross-socket PCIe as 10. This matrix is built once and kept in memory, so scheduling decisions can be made quickly. Next is the scoring algorithm. For a 2-GPU job where needs_peer equals true, the scheduler enumerates all possible GPU pairs. If there are 4 GPUs, that means C of 4, 2 equals 6 candidate pairs. It checks the score of each pair in the matrix and simply picks the highest scoring one. It is a brute force approach, but for systems with 16 GPUs or fewer, it is perfectly reasonable. Now moving on to queuing and priority. The scheduler maintains 2 queues, a pending queue for new jobs and a waiting queue for jobs that are currently blocked because resources are not available. When a running job finishes and GPUs are freed, the scheduler retries the waiting queue first, which helps prevent starvation. Priority is also supported. Lower number means higher priority, and if priorities are equal, submission time is used as the tiebreaker. Next is process isolation. Each job is launched using fork, then setsid, and finally exec_vp. The purpose of setsid is to create a new process group, so if a timeout happens, the scheduler can terminate the entire process tree, not just the parent process. For timeout enforcement, it first sends sigterm, waits for 10 seconds, and if the job still does not exit, it sends sigkill. And this leads to an important design constraint. The scheduler never touches PyTorch, tensors, or model logic. It is completely framework agnostic. Its responsibility is only to assign the right GPUs, set environment variables, launch the process, and monitor it. So overall, this system acts like a lightweight GPU-aware scheduler that makes better placement decisions automatically, especially for distributed and communication-heavy workloads. That's the main idea. I have tried my best to explain it clearly through the diagram. The GitHub link is in the description if you want to check out the project. I will also add a quick demo video of it soon on Vast AI GPU of Hugging Face fine-tuning and inference. Thanks for watching, and if you have any suggestions or improvements, please let me know.